So we're going to look at Introduction to Manufacturing Processes. This is a two-part thing, and so you should have the notes that were at the bottom of the link for this video open while you are watching this. So first of all, there are different types of processes we need to look at. There's primary and secondary. Before something is manufactured, there has to be some raw materials to be made into the usable materials. And they're generally renewable or they are exhaustible. Renewable would be things like trees, cotton, wool, animal products. Exhaustible are things that cannot be replaced, like metal, ore, petroleum, natural gas, coal. They just take too long to have been created in the first place, so they are considered non-renewable or exhaustible. A primary process, a pretty significant piece here, is the point at which raw materials are changed into a usable material. So the raw petroleum is changed into the usable gasoline or the usable oil or whatever you're using. And the secondary process is taking the usable material and using it to create an actual product, like casting and molding or forming something by bending it or separating things or attaching, joining things together, assembling, finishing. Those are all secondary processes that we're going to take a look at. So in general, the manufacturing process looks something like this. You have an input, people put stuff into a system, the system receives outputs and achieves its goals. The process is where the actual work is done. It generally transforms things. It deals directly with the input, transforms them in the process, and the output is something that's a manufactured product. Other outputs can be to include scrap, pollution, noise, fumes, etc. Those are some outputs, not the ones that you desire, but generally the output is the thing that you desire. And then any feedback is something that can be used to sort of control the system. So if you think about the thermometer, if the temperature gets hotter, if that's the output, then a thermostat might see feedback and say, okay, we need to turn it off. And then it's looking for a new input, and then it might be heating again and checking feedback and so on. So we've looked at this flowchart, this idea before with respect to input, process, output, and feedback. So that should be relatively familiar from earlier on in the year. Taking a look at materials, we'll look at a couple in specific here. Ceramics, metals, and plastics are generally well suited to manufacturing because ceramics are very hard, but ceramics are also brittle. So brittle means that if you apply a force to it, direct force to it, it can shatter. But ceramics are also heat resistant and they're corrosion resistant. So actually ceramics are really useful in the aerospace industry for rocket exhaust because it withstands a lot of high heat. There's not a lot of impact on an exhaust nozzle. So ceramics are good choices for that. Metals are any category of electropositive elements. They have a shiny surface, are generally good conductors. They can be melted or fused together. They can be hammered into thin sheets. That means that they're malleable. They can be drawn into wires, so metals are really useful. And plastics also, because plastics are materials that undergo a permanent change in shape or size when subjected to a certain amount of stress. So these are some common materials that we're actually going to take a look at some videos for. Properties determine what process that they're best suited for. So again, I was talking about ceramics for rocket engine nozzles. But you wouldn't want to use ceramics for like a hand sanitizer pump bottle. It's just not the most useful. Or a lotion bottle where you need to squeeze it, because you're not going to squeeze a ceramics bottle. Metal would also be bad for a lotion bottle, but plastics are good because they're a lot more malleable and flexible, I guess would be a better word for plastics. It can squeeze it, it's semi-elastic, so it will return back to its original shape. Whereas a metal sheet is not going to be elastic like that. So depending on what it is, the properties that you are looking for and in the product you're trying to design, that'll help you determine what type of material you want to use. So the first thing I'm going to have you take a look at is this composite video and use this to help answer any questions that are addressing this topic.
Composites are made up of at least two distinct intended materials which together improve product performance and/or lower manufacturing costs. Many materials routinely designated by other terms are also considered composites, including plated, clad, or coated metals. The term composite, however, has come to mean a material consisting of a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. The reinforcement's function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles.
Now we're looking at how you select materials. Materials are generally selected based on physical properties and like density, porosity, moisture content, things like that. Also mechanical different properties. If you want to look at number of types of imperfections in the material, the strength, plasticity, ductility, elasticity, hardness, all of these types of properties are really important if you're trying to design a material. And I'm not going to go into the details on any of those because it's not really the scope of what we're trying to do. But what you do need to know is that when you select a material, it really has to match the type of product that you're trying to design. So we're going to take a look at casting and molding first. This is a really common process for creating lots of one particular type of part, so bottle caps. Bottle caps almost all look the same, but they're different colors. So you might have one plastic injection molder, and you're going to see a video on that in a second, and then they just use raw plastic pellets of different colors to injection mold many of these other ones. So casting and molding are two different things that are used for plastics. Molding is just shaping it, shaping the raw plastic, whereas casting is melting it and then pouring it into something. So those are two big differences between casting and molding. And right now I want you to watch these three. They're going to be following.
Casting is the solidification of molten metal that is poured into a mold or injected into a die having a cavity in the shape of the desired part. Casting is used in virtually every industry, since all metals can be cast. Even mill forms, such as bar and plate, are produced from cast metal. Casting is usually the quickest way to shape metal into a part. Because of this, casting is used both for prototyping as well as production of large quantity parts. Casting processes can be grouped into three classifications: expendable mold, reusable pattern processes; expendable mold, expendable pattern processes; and permanent mold, no pattern processes. Which casting process to choose depends on part size, part configuration, part quantity, required tolerances, and the metal specified. Die casting is a rapid, high production process for simple or complex, often thin-wall, precision parts. Castings are usually small to moderate in size and cast of non-ferrous metals. The molten metal is forced under high pressure into the die of a horizontal, sometimes vertical, die casting machine. One die half is attached to a fixed platen, the other die half to a movable platen. Die casting can produce a single part or multiple parts in a single metal charge, also called a shot.
Injection molding is the most common method of producing parts out of plastic material. The process involves injecting molten plastic at high pressure into a mold shaped in the form of a part. Once this plastic cools and solidifies, the mold opens and the part is ejected. Injection molding is an extremely versatile process that can produce parts with holes, springs, threads, hinges, and undercuts in a single operation. Injection molded parts can be simple or complex and can be solid, foamed, reinforced, or filled. They can be small or large, thick or thin, flexible or rigid. Injection molded parts also lend themselves to endless decorative effects. They can be polished, textured, hot stamped, plated, colored, or clear. No other manufacturing process offers the range of capabilities injection molding provides. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. All injection molding machines are a combination of two systems, an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are two types of injection mechanisms: the reciprocating screw, which is the most common, and the two-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. The screw consists of 3 zones. The first zone, which is 1/2 of the screw, is called the feed zone. It has a constant flight depth, which forces the material together and rids it of air. The second zone, called the melt zone, has a decreasing flight depth, which reduces the plastic volume. This causes the plastic molecules to rub harder against each other, plasticizing the material. The melt zone leads to the third, or metering zone. The metering zone has a constant flight depth much smaller than that of the feed zone. This section acts as a pump. The tip of the screw has a one-way valve which lets the material flow only towards the nozzle end. The force of the plasticized material pushes the screw back as it turns. This builds a chamber of plastic in front of the screw. When enough material for the injection shot is melted, the screw stops and pulls back to decompress the material. For injecting the material, the one-way valve closes as the screw is hydraulically pushed forward by the injection cylinder. This sends the molten material through the injection unit's nozzle and into the injection mold. The primary speed and the injection pressure, called the packing pressure, is high, usually around 20,000 psi, but sometimes reaching up to 30,000 psi or higher. A secondary lower pressure is applied shortly after the initial injection. At the time of injection, the material's temperature ranges from approximately 320 to 600 degrees Fahrenheit, or 160 to 320 degrees Celsius. Once the plastic solidifies, no more pressure can be exerted upon it in the mold. The reciprocating screw then begins to rotate again, melting material for the next shot.
So you've just watched those 3 videos. We are now done with part 1. Make sure you got the notes on those sections, and you can pick up on part 2 to finish this assignment.